having me today. And I'm Pin-Ying Wu from Meteorology Research Institute. I'm now a postdoctoral fellow of JSPS in Japan. And this work is conducted with when I was in my PhD program with my advisor, Professor Tetsuya Takemi. So today I'm going to talk about the predictability of thunderstorms and the impacts of mountain topography and background flow on it. So I believe that all of us are already familiar with the scale-dependent predictability, especially after the great presentation from George Shaw. And so at the scale of thunderstorm, the predictability is considered strongly limited because of its small scale characteristic. And errors also grow rapidly with the development of moist convection. So predicting thunderstorm is very challenging. However, although we all know predicting thunderstorm is challenging, there's factors, for example, topography and background winds. These factors can affect occurrence or development of thunderstorm, but we poorly understand the impact of this factor on the predictability of thunderstorms. So in this study, we conducted idealized simulations, as shown by the animation here, of thermally induced thunderstorm, and conducted identical twin experiments to investigate the impact of topography and background winds on the predictability of thunderstorms. So in this study, we use Wolf model version 4 in an idealized configuration. The grid spacing is 1 kilometer with the horizontal domain size of 300 kilometers squared and 50 vertical wave levels. We use doubly periodical lateral boundary conditions, and here's the simulation, which is initialized from a real sounding data on a summer day in Japan. We added perturbation to temperature over low levels to initialize the simulation for 3 days. And here's the domain mean hourly rainfall of our simulation. We can see clear diurnal cycle in our simulations. And in the following, we take the simulation result on second day to conduct twin experiments. So here is the design of identical twin experiments to investigate predictability and error growth. We added small perturbation to water vapor at 6 o'clock in the morning before the convection starts to develop, and performed the perturbed simulation. So the differences between the control and perturbed simulation is seen as error and used to investigate the predictability. And of course, to investigate the impact of topography and background wind, we conduct 2 different experiments, one with mountain topography with Gaussian shape, and the other one we remove the background wind from the sounding. So and this excuse me. So these three animation shows the simulation results of in these 2 of control and perturb simulation in these 3 experiments. So we can see in the experiments with topography, we have a Gaussian shaped mountain over the left bottom area of the domain. So to quantitatively estimate the differences between the control and perturb simulation, which was seen as error in our experiment, we use a matrix called CNDTE, which can take into account the wind, temperature, water vapor, and surface pressure. Here's an example of the calculated CNDTE on the right-hand side. From when we have simulation of control and perturb run shown in the left, we the calculated CNDT is shown in the right-hand side. And we can see over the area of the development of convective clouds, generally the error is larger. So to take a look into more detail of the error growth associated with each convective cloud, we detected individual convective cells as shown by the red boxes here, and we calculate the size of clouds and the error in each individual cloud area, and plot the scatter plot here. So we can see at later times in general the error is larger, and at the same time when the size of cloud is larger, the error in that cloud area is also larger. And we do the same thing to the experiments of the with topography. And in general, we can see the core color plot here in these two experiments is very similar. However, there are some plots in warm color here, showing that these convective clouds have smaller errors compared to the other convective clouds with the same size developed other areas. So these plots in warm colors are actually the results of convective clouds developed over the mountain area in the morning. So here the results suggest that in the morning when the convective cloud developed over the mountain area, there's a topography effect on mitigating the error growth. So to figure out what makes the error growth slower here, we try to analyze the initiation convection initiation mechanism of the deep moist convection over the mountain. So here's the cross section of potential temperature anomaly. You can see there's a warm area on the lee side of the mountain, and this warm area is caused by the solar radiation heating. This warm area induced the upslope wind over the lee side, and this upslope wind converges with the background wind from the right-hand side. So this convergence induced the development of deep moist convection over the lee side of the mountain. This mechanism of convection initiation is considered less uncertain because if we have upslope wind here, the convection is likely to always develop over this location. So this might be the reason of the smaller error growth associated with the convective cloud over a mountain area. So in next part, this time we invested the predictability limit by performing some additional perturb simulations with smaller and larger initial errors, also starting the simulation at later times. So here, this figure shows the evaluation of errors for this additional perturbation run. We can see for every perturbed runs, the error growth and saturated at around 13 o'clock. This result suggests that in our case, our simulated thunderstorms, the predictability limit is at around 13 o'clock in the afternoon. And if we compare the result to the experiment with topography, which is plotted in orange, we can see that even in the experiment with mountain topography, the error growth and saturated at almost the same time as the experiment with without topography. So this result suggests that in our case the predictability limit changes little in the experiment with topography. So next, we compare the experiment with different background width. So the result is shown in purple colors here. And we can see clearly the purple curves here show earlier saturation time compared to the other two experiments. And if we further compare the activity of convective clouds, shown in the bottom figure here, we can see the saturation time of the arrow growth is generally corresponding to the maximum convective activity time. So here, our results suggest that the convectivity might be the key factor that determines the time of predictability of thunderstorms. So here's my summary. In this study, we conducted identical twin experiments with idealized sound simulation of thermally induced thunderstorms, and to investigate the impact of topography and background wind on the predictability. So we found that convection development greatly determine the arrow growth and predictability. For the impact of the background flows, we found that because background flows affect the time of maximum convective activity, so as a result, different background flows change the time of predictability limits of thunderstorm. On the other hand, mountain topography, in our case, show less impact on the maximum convective activity time. So there's also little impact on the time of predictability. However, topography in our case do show its effect on the arrow growth during the early stage of convection development by reduce the uncertainty of convection initiation mechanism. So there are two implications that I would like to share with you from our result. The first one is that our results suggest that we might need to think differently for the predictability at convective scales, different from the loss in synaptic scales. For example, our results show that the time of predictability limit did not change even starting the prediction at a later time, which is kind of different from the results shown in the synaptic scales. Another implication is that if we have an ensemble with only initial perturbation, because our results show that the arrow growth is smaller over the mountain area. So this ensemble might underestimate the background errors over the mountain areas if we only have initial perturbations. And we have other experiments with different mountain heights, winds, and we also discussed rainfall predictability in our paper. If you are interested, you can refer them. So this is all I have today. Thank you for your attention.
Thank you very much, Pin-Ying. I wanted to ask the members of the audience if there are any questions to the presentation.
Okay. Should I? Okay. Will you read out?
I'm not sure which question we're talking about now.
I see the question from George.
Yes, so there is a question from George. Interesting results. Have you computed energy spectra for your experiments with different amounts of convection? Is the error growth in the convection experiments locked to the diurnal cycle?
Oh yeah. We did compare the energy spectra. Is the error growth in convection locked to the diurnal? Yeah. Yes. So all results I showed today is only the simulation, the result of twin experiments for 1 day. after the line, so the arrow just goes to up to saturation. If you see the curves here, this is actually at the 9 of this day, and it the arrow actually decreased a little bit and at 9 and goes again in the second day in the morning when the thunderstorm again to develop. So this is the answer for the second question, and the first question is arrow spectrum with different amounts of convective. So we basically we have the almost we use only one sounding data to initialize our experiment. So basically the background in environment condition is very similar. So we actually do not have very different convection amounts. If you show the convective activity shown in the dashed curves here, the maximum activity is all actually very similar. So we do not have experiment to show the spectrum of different convection amount. And I believe there's another question from Ihan. She said they have seen this effect for install. Oh, that's I believe you mean the different physics parameterization. And so we didn't do that kind of experiment, but I believe that the effect, for the impact of static schemes should have some impact on that. And if you do use different schemes, the result should be different. But I don't have answer on it, so thank you.
All right, thank you very much, Pin-Ying.